Picture this: two identical-looking race cars sitting at the starting line. Same engine displacement, same horsepower, same tire compound. The Christmas tree drops and both drivers nail absolutely perfect launches. Through first gear, they're mirror images of each other, nose to nose, fender to fender. Then something happens that shouldn't be possible. One car suddenly rockets ahead by 3 car lengths in the space of a single heartbeat. Not from a hidden nitrous system, not from illegal modifications, not from some secret fuel blend. From how fast the transmission shifted gears. That's it. That single variable, the time between gears, created a gap that looked like cheating but was pure innovation. This is legacy motoring, and I spend way too much time thinking about the hidden advantages that separate winners from everyone else. If you're someone who obsesses over the engineering secrets that dominated motorsports, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Here's the thing about drag racing in the 1980s. Everyone was chasing horsepower. Every team was spending thousands of dollars trying to squeeze another 10 or 15 horsepower out of their engines. They were experimenting with exotic camshaft profiles, custom intake manifolds, and radical cylinder head porting. The horsepower wars dominated every conversation in every pit area across the country. But one guy from Ohio saw something everyone else was missing. He realized that horsepower meant absolutely nothing if you couldn't deliver it to the track consistently. And the biggest thief of that power delivery wasn't the engine, it wasn't the tires, it wasn't even the aerodynamics. It was the transmission. Bob Glidden wasn't supposed to be a legend. Born in 1944 in Whiteland, Indiana, he didn't come from racing royalty. His father wasn't a famous crew chief, his family didn't own a speed shop. He started racing in the 1960s with a 1962 Ford Galaxy that he built himself, in a garage that leaked when it rained. Most people would look at that and see limitations. Glidden saw opportunity. Now, you might be thinking that transmission speed couldn't possibly matter that much in a quarter-mile drag race. I get it. When you watch a pro stock race, everything happens so fast that human perception can barely keep up. How could fractions of a second between gears make a meaningful difference? Here's what most people don't realize. During a shift, your car is essentially coasting. The engine is spinning and making power, but that power isn't reaching the wheels. It's lost in the transition between gears. And at pro stock speeds, coasting for half a second equals about 60 feet of distance. That's 4 car lengths per shift. Let me put that in perspective with some numbers that might blow your mind. A stock Ford C6 transmission, the bulletproof 3-speed automatic that Ford introduced in 1966, shifted gears in approximately 0.5 to 0.6 seconds. That was by design. Ford engineers deliberately programmed overlap between gears to create smooth, comfortable shifts. Your grandmother could drive a C6-equipped Lincoln to church without spilling her coffee. That smoothness was a feature, not a bug. Except in drag racing, that smoothness was death. The C6 was Ford's heavy-duty automatic, engineered to handle the massive torque of their 428 Cobra Jet and 429 Boss engines. It used a cast iron case, oversized planetary gears, and clutch packs with enough surface area to survive decades of abuse. Ford designed it to tow boats, haul trailers, and cruise highways for hundreds of thousands of miles. The gear ratios told the story of its intended purpose. First gear was 2.46 to 1, second was 1.46 to 1, and third was direct drive at 1 to 1. Those wide ratios were perfect for everyday driving and commercial applications. Here's where it gets really interesting. Those same design choices that made the C6 perfect for street duty contained hidden potential that Ford never imagined. The large clutch packs meant more surface area for friction material. The simple planetary gear set allowed for faster ratio changes if you could control the engagement precisely enough. The straightforward valve body was easier to modify than GM's more complex designs. Ford had accidentally created the perfect platform for racing modifications. They just didn't know it. What Bob Glidden did over the next several years would fundamentally change how everyone thought about automatic transmissions in racing. He didn't just modify his C6, he completely reimagined what it could do. And his methods were so counterintuitive, so opposite to everything Ford engineers believed about smooth shift quality, that competitors spent years trying to figure out his secret. When they finally did, they couldn't believe something so simple had been beating them at every track across the country. Look, I've researched hundreds of racing innovations for this channel, and what separates Glidden's discovery from most others is how accessible it was. He didn't need wind tunnels or computer simulations. He didn't need metallurgical laboratories or aerospace engineers. He needed a die grinder, a deep understanding of hydraulic systems, and the willingness to push components in directions their designers never intended. That combination of technical knowledge and pure determination created an advantage that lasted nearly a decade in a sport where advantages typically last a few races before competitors catch up. The story of Glidden and his C6 transmission is really a story about seeing potential where everyone else sees limitation. Ford's engineers looked at the C6 and saw a successful product that did exactly what it was designed to do. Glidden looked at the same transmission and saw wasted time, unnecessary compromises, and untapped speed hiding in the spaces between gears. Both perspectives were technically correct, but only one of them won championships. The valve body is essentially the brain of any automatic transmission. It's an aluminum casting roughly the size of a pizza box filled with intricate passages, chambers, and spring-loaded valves that direct hydraulic fluid throughout the transmission. When you press the accelerator, throttle pressure signals the valve body to shift at specific RPM points. When those shift commands execute, hydraulic fluid flows through carefully sized orifices to engage clutch packs and bands that lock different elements of the planetary gear set. Ford's engineers had designed those orifices with deliberate restrictions. Think of it like putting your thumb over a garden hose. The restriction controls flow rate, which controls how quickly the clutch packs engage. Slower engagement meant smoother shifts. The valve body also contained check balls, small steel spheres that blocked certain passages during specific operating conditions to prevent harsh engagements. Every element was calibrated for comfort, durability, and refinement. Glidden started with a die grinder and carbide bits. Working methodically through the valve body, he enlarged critical orifices by thousandths of an inch at a time. He removed check balls that served no purpose in racing applications. He modified spring tensions on accumulator pistons to reduce their dampening effect. Each modification allowed hydraulic fluid to flow faster with less resistance. But here's what separated Glidden from other racers attempting similar modifications. He understood that faster fluid flow alone would destroy conventional clutch materials. Stock C6 clutches used organic friction material, essentially paper-based compounds bonded to steel plates. These materials needed gradual engagement to grip properly. Hit them with a sudden blast of hydraulic pressure, and they would either slip uselessly or grab so violently that something downstream would break. The output shaft, the drive shaft, the ring and pinion gears, something would absorb that shock and fail catastrophically. Most racers who tried aggressive valve body modifications learned this lesson the hard way through expensive parts scattered across pit lanes. Kevlar had recently emerged as a viable friction material for racing clutches. The same aramid fiber technology used in bulletproof vests possessed remarkable properties when formed into clutch discs. It could absorb massive clamping forces instantly without slipping. It didn't require gradual engagement to grip. You could slam full hydraulic pressure into Kevlar clutches and they would bite immediately without destroying themselves. The material also dissipated heat effectively, which mattered when you were asking clutch packs to do brutal work multiple times per race day. Glidden sourced custom Kevlar friction discs from a specialty manufacturer and rebuilt his C6 clutch packs from scratch. But Kevlar's instant grab capability was worthless without the hydraulic pressure to exploit it. Stock C6 transmissions operated at approximately 90 to 150 psi line pressure, depending on throttle position. That pressure was adequate for smooth street shifts, but nowhere near aggressive enough for what Glidden had planned. He modified the pressure regulator valve, essentially reprogramming how the transmission regulated its internal hydraulic pressure. He installed a higher capacity pump with tighter internal clearances that could generate more flow at higher pressures. His modified C6 now ran at 250 psi minimum, spiking to over 300 psi during shifts. That's roughly double the pressure Ford ever intended for this transmission. The physics of what happened inside Glidden's C6 during a shift were violent and beautiful simultaneously. When the valve body commanded second gear, those unrestricted passages allowed 300 psi of hydraulic pressure to slam into the second gear clutch pack, essentially instantaneously. The Kevlar clutches bit with zero slip, zero overlap, zero gradual engagement. The transmission transitioned from first gear to second gear in approximately 0.1 seconds, faster than a human blink reflex. Compare that to the numbers we discussed earlier. Stock C6 shifted in 0.5 to 0.6 seconds. A well-prepared race C6 with typical modifications might achieve 0.3 seconds. Glidden had found 0.4 of a second that everyone else was leaving on the table. Over 2 shifts per run, that translated to nearly half a second of total advantage. In pro stock racing, where margins of victory were often measured in hundredths of a second, half a second was a chasm. The first test session revealed unexpected consequences. When Glidden launched his Thunderbird and hit the 1-2 shift, the car behaved like it had been rear-ended at highway speed. The front wheels lifted slightly from the rotational forces being suddenly redirected. The tires chirped audibly despite traveling over 100 miles per hour. The entire chassis shuddered as if something had broken catastrophically. His crew chief immediately signaled to shut it down, convinced they had destroyed the transmission or snapped the drive shaft. They pushed the car back to the trailer expecting to find carnage. Instead, they found an intact drivetrain and a time slip showing the fastest elapsed time Glidden had ever recorded. Nothing was broken. The violence was working. This is where it gets really interesting from a competitive standpoint. The 1986 NHRA Winter Nationals at Pomona became the public debut of Glidden's advantage. Watching from the stands or even the competitor staging lanes, nothing looked different about his Thunderbird. Same body, same engine sound at idle, same launch procedure. But when that car hit the 1-2 shift, everyone noticed something was wrong. Or rather, something was impossibly right. Where other pro stock cars had a brief but audible drop in engine note during shifts, Glidden's engine note barely changed. The shifts were so fast that the engine didn't have time to lose significant RPM. Competitors described it as sounding like a power glide or a direct drive car, but that was impossible under NHRA rules. The tech inspectors started paying very close attention. After Glidden's victories that weekend, NHRA officials conducted thorough teardowns of his transmission. They measured every component, checked every passage diameter, verified every part against the rulebook. They found absolutely nothing illegal. The rules permitted internal modifications to manufacture correct transmissions. Nothing specified how fast those transmissions were allowed to shift. Glidden had read the rulebook more carefully than the people who wrote it. Word spread through pit lanes and hotel bars that Glidden had found something. Competitors didn't know exactly what, but the evidence was undeniable on every time slip. Cars with similar or even superior horsepower were losing to the Thunderbird by margins that defied explanation. The transmission was the only variable nobody had seriously considered. Newton's third law doesn't care about your championship aspirations. Every action has an equal and opposite reaction, and Glidden's violent shifts created forces that had to go somewhere. The energy of suddenly stopping one rotating mass while engaging another transferred through the drivetrain like a shockwave. Drive shafts twisted under loads they were never designed to handle. U-joints cracked and failed. Ring and pinion gears in the rear axle developed stress fractures from repeated impacts. Glidden's crew developed a rebuild schedule that would have seemed insane to any other team. They were replacing drive shafts every 3 or 4 runs, not every race weekend, every 3 or 4 passes down the quarter mile. U-joints became consumable items like spark plugs or brake pads. The transmission itself required complete disassembly and inspection every 5 or 6 runs, because even Kevlar clutches couldn't survive unlimited punishment at those pressure levels. The financial burden was significant. Where other teams might go through one transmission per season, Glidden was essentially rebuilding his every weekend. Clutch packs, seals, bearings, and friction materials added up quickly. Driveshaft bills alone would have bankrupted a less committed team. But Glidden viewed these costs as investments rather than expenses. Each destroyed driveshaft represented another win, another championship point, another step toward dominance. The human cost was harder to quantify, but equally real. Driving that Thunderbird was physically punishing in ways that modern safety equipment has largely eliminated. Each shift felt like being rear-ended by a truck. The driver's head would snap forward against the restraint system. Internal organs would compress momentarily from the deceleration, then acceleration forces happening within a tenth of a second. The shoulder harness would dig into chest muscles with enough force to leave bruises that lasted for days. After a full day of qualifying rounds and elimination passes, Glidden would climb out of that car looking like he had been in a boxing match. His neck would be sore for the entire following week. His chest would be marked with harness-shaped welts. Other drivers who attempted similar transmission modifications often abandoned the approach simply because they couldn't tolerate the physical punishment. Glidden accepted it as the price of winning. Here's what most people don't realize about the psychological aspect of competition at this level. Other drivers knew something was different about Glidden's car. They could hear it. Those shifts sounded wrong to experienced ears. The engine note should drop during gear changes as RPM falls, then climb again as the new gear engages. Glidden's engine note was almost continuous, like the transmission wasn't really shifting at all. Standing in the staging lanes waiting for your turn to race against him, that sound got inside your head. Warren Johnson, one of the most technically brilliant racers in pro stock history, spent countless hours trying to decode what Glidden was doing. Johnson ran GM equipment, so he couldn't simply copy Glidden's C6 modifications to his Turbo 400. But he studied time slips obsessively, comparing trap speeds and elapsed times, looking for the telltale signatures of where Glidden was gaining his advantage. The data told an impossible story. Glidden wasn't winning on launch. He wasn't winning on trap speed. He was winning in the middle of the track, during transitions that should have been neutral. Lee Shepard, another elite competitor, actually approached Glidden at a race and asked directly what was different about his transmission. Glidden smiled and said something vague about attention to detail. Racers guard their secrets jealously, and Glidden had no obligation to educate his competition. Shepard walked away frustrated but more certain than ever that the transmission was the key. The most fascinating reaction came from Ford's own engineering staff. The story circulating through racing circles is that a group of transmission engineers from Ford's Livonia plant attended an NHRA national event specifically to observe Glidden's car. These were the men who had designed the C6. They knew every passage diameter, every spring rate, every engineering decision that went into that transmission. They had spent years perfecting smooth shift quality for customer satisfaction. When they watched Glidden's Thunderbird make a pass and heard those violent, instantaneous shifts, they reportedly looked at each other in disbelief. That shouldn't be possible with C6 architecture. The transmission they designed had deliberate mechanical limitations that should have prevented shifts that fast. One engineer later described the experience as watching someone teach her dog to speak French. Theoretically impossible, yet there it was, happening in front of them. After the race, these engineers apparently requested permission to examine Glidden's transmission. What they found both impressed and horrified them. Glidden had essentially reversed their design philosophy. Every decision they made for smoothness, he had undone for speed. Every passage they restricted for comfort, he had opened for aggression. Every calibration they tuned for refinement, he had retuned for violence. One Ford engineer reportedly said that Glidden had turned their limousine into a rocket sled. The most interesting technical observation from these engineers was that Glidden's modifications wouldn't work on a lesser platform. The C6's oversized components, originally specified for durability and longevity in commercial applications, were what allowed it to survive the abuse. A lighter transmission with smaller clutch packs and thinner shafts would have grenaded immediately under those forces. Ford's conservative engineering, their tendency to overbuild everything, had accidentally created the perfect racing foundation. But Ford couldn't learn anything applicable to production vehicles from Glidden's work. No customer wanted shifts that violent. It would generate massive warranty claims, potential injury lawsuits, and universal customer dissatisfaction. The modifications existed in a space that only made sense for pure competition, optimized for a single purpose with no compromise for any other consideration. This is why racing innovation and street car development often follow parallel but separate paths. Glidden captured the 1986 NHRA Pro Stock Championship by a comfortable margin. His Thunderbird was simply faster than everything else in the class, and the consistency of his shift advantage meant he could afford minor mistakes in other areas and still win rounds. The following year brought the same result. 2 consecutive championships built substantially on an advantage that competitors still hadn't fully decoded. By 1988, whispers were becoming conversations. Racers who had been beaten by Glidden repeatedly started piecing together the puzzle through observation and deduction. The transmission building community in drag racing was remarkably small in the late 1980s. Perhaps 24 specialists across the country handled the majority of pro stock and professional-level automatic transmission work. They talked to each other at races, shared observations over beers, and compared notes on what worked and what failed catastrophically. Information moved through this network slowly, but inevitably. A transmission builder named Art Carr had been studying Glidden's time slips for 2 seasons. Carr ran a shop in California that served numerous West Coast racers, and his customers kept asking why their cars couldn't match Glidden's mid-track acceleration. Carr started experimenting with valve body modifications on his test bench, using hydraulic flow meters and pressure gauges to measure exactly what happened during shift events. His breakthrough came when he realized the relationship between orifice size, pressure, and clutch engagement timing was nonlinear. Small changes in the right places created massive changes in shift behavior. By late 1988, Carr was offering what he called competition valve bodies to select customers. These weren't quite as aggressive as Glidden's personal specifications, but they represented a significant step toward closing the gap. Other transmission builders reverse-engineered Carr's work and developed their own versions. The technology was spreading. Warren Johnson finally cracked the code for GM applications. His Turbo 400 transmissions had different architecture than the C6, with smaller clutch packs and different hydraulic routing, but the fundamental principle remained identical. Increase line pressure dramatically, use aggressive friction materials, remove all dampening from the valve body, and accept the consequences. Johnson's Oldsmobiles started exhibiting the same violent shift characteristics that had made Glidden famous. Chrysler teams working with the torque flight transmission faced greater challenges. That transmission's design included a more complex gear set that was inherently slower to transition between ratios. No amount of valve body modification could completely overcome architectural limitations. This disparity actually influenced manufacturer participation in pro stock during this era, as racers gravitated toward platforms with better modification potential. The shift speed arms race escalated rapidly once the secret was public knowledge. By 1990, teams were pushing beyond what Glidden had achieved just 4 years earlier. New friction materials emerged that could handle even higher clamping pressures. Exotic pump designs generated line pressures approaching 400 psi. Valve bodies became so aggressively ported that they would barely function at normal operating temperatures and required extensive warm-up procedures before making passes. NHRA officials watched this escalation with growing concern. The violent shifts were creating secondary problems that affected everyone at the track. When a car shifted that hard, the sudden weight transfer drove the rear tires into the track surface with tremendous force. This was deforming racing surfaces and creating safety hazards. Some tracks reported visible ruts in their concrete where pro stock cars made their 1-2 shifts weekend after weekend. Driveline failures increased dramatically across the class. When transmission shifted in under 0.2 of a second, components downstream experienced impulse loads that exceeded their design limits. Drive shafts exploded into fragments that could penetrate floor pans or fly into adjacent lanes. Ring and pinion failures sent debris across racing surfaces. Safety crews found themselves cleaning up mechanical carnage more frequently than ever before. The sanctioning body implemented new rules in the early 1990s attempting to regulate shift speeds. These rules required specific minimum shift times measured by onboard data recorders. Teams had to submit their transmission specifications for approval. Any modification that resulted in shifts faster than the mandated minimum would result in disqualification. The rules were controversial because they essentially penalized innovation, but NHRA justified them on safety grounds. Here's where it gets really interesting from an engineering evolution perspective. The shift speed limitations didn't stop transmission development, they redirected it. Instead of pursuing ever faster shifts, builders began optimizing consistency. If every team was limited to the same shift speed, the advantage went to whoever could hit that exact number most reliably under varying conditions. Temperature changes, clutch wear, and hydraulic fluid degradation all affected shift timing. The teams that controlled these variables most precisely gained the edge. This consistency focus actually produced better racing. When shift speed was unlimited, the team with the most aggressive transmission usually won regardless of other factors. With shift speed regulated, driver skill and other vehicle setup parameters mattered more. Races became more competitive because the playing field was more level. Glidden continued winning through the 90s, but his margins of victory shrunk as competitors achieved parity in transmission performance. The ripple effects extended far beyond NHRA Pro Stock. Formula One teams had been developing electro-hydraulic sequential gearboxes since the mid-1980s, but watching what American drag racers achieved with relatively primitive technology accelerated their development timelines. If an Ohio racer with a die grinder could cut shift times by 80%, what could Ferrari and McLaren accomplish with unlimited budgets and aerospace engineering resources? The Ferrari F1 team introduced their 7-speed semi-automatic transmission in 1989, featuring paddle shifters and hydraulic actuation that allowed drivers to change gears in under 50 milliseconds. This technology eventually migrated to Ferrari's road cars, and then to the broader automotive industry. Every modern dual-clutch transmission owes conceptual debt to racers who proved that shift speed mattered. NASCAR teams paid attention despite running manual transmissions. Drivers began practicing synchronized downshifts and upshifts designed to minimize time between gears. Crew chiefs experimented with different gear ratios to reduce the number of shifts required per lap. The entire philosophy of momentum maintenance through gear changes became a significant competitive factor in stock car racing. Even the American muscle car aftermarket absorbed these lessons. Street performance enthusiasts who previously focused exclusively on engine modifications started considering transmission upgrades as power delivery systems rather than just power handlers. Valve body kits, shift improvement packages, and high-stall torque converters became standard recommendations for anyone building a performance vehicle. The community's understanding of what made a car fast had evolved. The transmission technology that Glidden pioneered became standardized equipment within a decade of his initial innovations. What seemed radical in 1986 was mandatory for competitiveness by 1996. The cycle of innovation, advantage, imitation, and standardization played out exactly as it does in every competitive arena. But the speed of that cycle, from secret weapon to industry standard in roughly 10 years, demonstrated how significant the original discovery was. Bob Glidden retired from professional competition in 1997 with a record that still impresses anyone who understands pro stock racing: 85 national event victories, 10 NHRA championships across multiple decades, countless round wins against the best drivers and teams in the sport. Those numbers alone would secure his place in motorsports history, but the transmission innovations represent something more significant than any trophy count could capture. The philosophical shift that Glidden introduced changed how engineers and racers think about mechanical systems. Before his C6 modifications gained attention, the prevailing wisdom treated transmissions as necessary evils. They existed to connect engines to wheels, nothing more. You maintained them, you kept them from breaking, and you focused your development energy elsewhere. Glidden proved that transmissions were active participants in performance, not passive connectors. Every component in the drivetrain either helped or hindered your elapsed time. Nothing was neutral. Modern pro stock racing runs purpose-built Liberty 5-speed transmissions that shift in approximately 50 milliseconds. That's half the time Glidden achieved with his modified C6 using 1960s technology and hand tools. These contemporary units use computer-controlled solenoids, exotic metallurgy, and friction materials developed specifically for instantaneous engagement. They represent 40 years of concentrated development, building on foundations that racers like Glidden established. Here's what most people don't realize about technological progress in racing. The gap between Glidden's 0.1-second shifts and today's 0.05-second shifts required exponentially more investment than his original breakthrough. He found 0.4 of a second using creativity and determination. Finding the next 0.05 required millions of dollars in research, development, and material science. The low-hanging fruit of innovation is always the most valuable because it costs the least to harvest. The C6 transmission itself became a cult object in Ford performance circles. Despite being officially obsolete since Ford discontinued production in 1996, these transmissions remain popular in bracket racing, nostalgia events, and street strip applications. Enthusiasts rebuild them using techniques directly descended from Glidden's methods. Aftermarket valve bodies advertised as competition spec or race prep trace their design philosophy to that Ohio garage where a racer with a die grinder rewrote Ford's engineering specifications. Transmission builders who learned their craft during the shift speed wars of the late 80s and early 90s now train the next generation. They pass along knowledge that was once closely guarded secrets, teaching apprentices about pressure curves, clutch engagement dynamics, and the relationship between hydraulic flow and mechanical response. This knowledge transfer ensures that Glidden's insights continue influencing the sport decades after his retirement. The broader automotive industry absorbed these lessons through indirect channels. Modern dual-clutch transmissions like Porsche's PDK and Volkswagen's DSG shift in under 8 milliseconds on street cars. These systems pre-engage the next gear before releasing the current one, essentially eliminating the power interruption that Glidden worked so hard to minimize. The engineering priority of reducing shift time became standard practice because racers demonstrated its value in competition. Even electric vehicles carry forward this philosophy despite having no traditional transmissions. Tesla's single-speed reduction gearing eliminates shift events entirely, representing the ultimate expression of zero power interruption during acceleration. Engineers designing these systems cite Motorsports development as inspiration for prioritizing continuous power delivery. The connection between a 1980s drag racer and modern electric performance might seem tenuous, but the conceptual lineage is clear. What made Glidden's achievement remarkable was its accessibility. He didn't need wind tunnels, supercomputers, or teams of specialists. He needed mechanical understanding, systematic experimentation, and the courage to push hardware beyond its design parameters. This democratization of innovation remains possible even in an era of increasing technological complexity. The most important advances often come from individuals who see possibilities that institutions miss. The story also carries a warning about the temporary nature of competitive advantage. Glidden dominated for 2 seasons before competitors caught up. His secret spread through the racing community despite his efforts to protect it. By the time the 1990s arrived, what he pioneered had become standard practice. Innovation creates advantage, but advantage attracts imitation. The cycle repeats endlessly in every competitive field. Glidden passed away in December 2017 following injuries sustained in an automobile accident. The racing community mourned a champion whose influence extended far beyond his personal victories. Tributes poured in from competitors who had raced against him, from transmission builders who studied his work, and from enthusiasts who had watched his Thunderbird dominate tracks across the country. His legacy lives in every violent shift, every pursuit of efficiency, every racer who refuses to accept that something cannot be improved. When you watch a modern pro stock car launch and rip through its gears with barely perceptible pauses, remember the man who made that possible. Remember that those millisecond shifts descend from modifications made in an Indiana shop by a self-funded racer who outthought factory engineers. Remember that innovation doesn't require unlimited resources. It requires seeing potential where others see limitation and having the determination to prove your vision correct. What's your experience with high-performance transmissions? Have you ever felt those brutal racing shifts that compress your spine and snap your head forward? Drop your thoughts in the comments below. And if this deep dive into drag racing innovation delivered value, hit that subscribe button for more stories about the rebels who refused to accept conventional wisdom and changed motorsports history through pure ingenuity.